And this step by himself is an inverse problem. This step by himself is an inverse Fourier transform. Actually, let me write it here. Let me write it here. F of x inverse Fourier transform is integral of f of omega x omega y exponential of plus the same thing d omega x d omega y. Okay. Could you see? Okay, so let me start this and then I will show you. So this is, what is now interesting is that if in place of X-rays, if you had put here microwave, and you could send a microwave, a plane wave of microwave. This microwave goes inside the body, and here what you can measure is called diffracted wave. And again, the equations are too much complicated to write it here. But what would be interesting is that in the case of microwave, again, within the Born approximation and linear approximation, again, you can relate the one-dimensional Fourier transform in the two-dimensional Fourier transform of the object, but this time the relations are not on a line, but on a semicircle. So it means that this part, for the case of microwave, this part would be something which, in place to be on this line, will be on this semicircle. The values will be on this semicircle. And the diameter of this semicircle is inversely proportional to the wavelengths. And you can understand that for the X-rays, the wavelength is very short. So the diameter of this circle is huge. So this becomes a line, a straight line. So, but the same principle can be applied. And this time you will have this circle, these semicircles, and so on. And again, the same technique can be applied for image reconstruction. This is very, very interesting relation between the X-ray tomography and microwave or ultrasound tomography. And mainly these relations I have written here. Actually, this is also an inverse problem. If I knew the value of f everywhere, then there wasn't any problem. I could do this integration. Fourier, which was a French mathematician who showed this relation, Fourier showed that if I know the value of f everywhere, then I can find this expression. But what happens if I do not know everywhere? If I do not know the values of the Fourier transform everywhere, I know them only on some lines or on some semicircles. I do not know them everywhere, a limited number of angles. Then the problem again is ill-posed. The problem is again ill-posed, but however, this Fourier inversion is called an analytical method of inversion and can be applied. So this Fourier synthesis is also an example of inverse problem that we have studied. And what is interesting again for this inverse Fourier synthesis problem is that this problem arises in many other applications, and in particular, for example, in SAR imaging, synthetic aperture radar imaging. You can also show that when you have a scene with some object here, if you choose the airplane who goes on this straight line, and at each position of the airplane, here you send a radar signal. This radar signal goes and hurts the scene, comes back, and it is possible to show, and it is not time to go in details of this application. Probably later I will come back on this application. But it is possible to show that mathematically, if you go through all the equations of this radar imaging, and for each angle theta, you send a radar signal. Signals come back. The signals which come back, if you compute its Fourier transform, it's a spectra, it is possible to show that the spectra of the signal, which is here, can give you some information in the Fourier domain, omega x and omega y. This is f of x and y on some line. This line makes an angle. Okay. This line makes an angle theta. This is the angle theta, I think, if I remember exactly. This line makes an angle theta with the axis, and this length is related to the bandwidth of the signal, radar signal, which has been sent to the scene. Okay? So you have the bandwidth of the signal, emitted signal, you have the angle, and when the airplane changes the position, the angle changes. For different angles, for another angle you will have this, for another angle you will have this, and so on. Okay? And if you can, because it is symmetric in this case, you can see that you can have the Fourier values here, so you have finally a band of Fourier data. And in radar imaging, actually the mathematical problem is what? The mathematical problem is that you know the values of f of omega x and omega y. You know the values of this function. Only on this band. You do not know it at other places. And you want to find the scene. You want to make an image of the scene. So this relation between this and this is a Fourier transform relation. So the inverse problem, which is going from partial knowledge of f, obtain f. This is the inverse problem of SAR imaging. Okay? Inverse problem. I call this inverse problem Fourier synthesis. So Fourier synthesis inverse problem. Fourier synthesis inverse problem in SAR imaging. Actually, the problem is more sophisticated. To obtain these relations that I have written here, there has been done a lot of hypotheses. For example, it is assumed that the sen is just the points, the point sources. There is not interaction between the interaction between the sources has been neglected to obtain this mathematical relation. So the real SAR imaging problems are more sophisticated. If we want to take to account for all the equations exactly, is more sophisticated. But if we do some simplification hypothesis, then we can arrive at this mathematical inverse problem. Okay? And what is still more interesting is that this Fourier synthesis problem arises in many other imaging systems, in radioastronomy, in geophysics, in non-destructive testing, etc., etc. Let me show a few transparencies on that. Can we now put yes, it is possible to. Any questions or remarks on these informations which are on the table? We have to open it, this, yes? Where is that? Please do not hesitate to ask the questions. No. Validate. Normally it is no. No, it is good. 13. Photo.
If I have some advice, maybe there's only 5 minutes to.
Okay, we can do it at the. Okay. So that would be. So I will show these slides just after the break because we do not have too much time. Okay. Any questions up to here? So if I can summarize these things. Now, let me start by this part. Yeah, one last point on this tomography application was we have started yesterday. Was discretization of the problem. For this, let me take again this function f of x and y, and this time we are going to assume that this function can be discretized in pixels, okay? this is exactly what we mean by discretization. So if we discretize this space, it means that the function f is assumed to be constant in each of these pixels. Okay? So when I have a position here of the source, and when I have a position of the detector here, to compute this integral, which is, if you remember, g of r and phi, was written f of x and y, dl, and dl, it was an element of the length. Okay? So this means that if I assume that the function f is constant in this area, and I call the value of the function f1, f2, f, etc. up to fn, f1, f2, f3, f4, etc., 5, 6, 7, and so on. And if I call this gi, gi is integral is sum of what? Sum of the values of f multiplied by the length L. For example, if I take this pixel, if I call it f and xj, and if I call this length from here to here hij, then I have here hij, fj, and sum is over j. Can you imagine that? So you see that this integral equation can be transformed to a sum. Integral here becomes a sum. The elements of dl, you take this length, hij. Hij is the length of the ray number I in the pixel j. Length of the ray I in pixel j. So you can see that the relation that it is written here can be finally transformed to this sum, and this relation finally we can write it g equal to hf, again in discrete form. Okay? And what we can, all the things that we have explained before can be explained again in this discrete form. So here we were talking about this, and now as one of the exercises that I am going to give you is, let's try a very simple case where we have only 4 pixels, an image of 4 pixel by 4 pixel. This is just to show what happened. In general, we have 1000 by 1000 pixels, but this is important just to see what is going to happen. If I note the value of the function here, f1, f2, f4, f5, and f6, 16. Okay? And if I note the values of the projection at this value g1, the value at this position g2, the value at this position g3, and the value here g4. So these are the projections, and let's assume that we have only 2 projections. Okay, two projections at angle 0 and angle 90 degree. And I'm going to call this G5, G6, from here, G5, G6, G7, and G8. So can you write G1, G2, G4, G5 up to G8? If you form this matrix, here F1 up to F16, can you tell me that G1, what will be the elements of this matrix? G1 will be equal to F1 multiplied by this length, F2 multiplied by this length, F3 multiplied by this length, F4 multiplied by this length. We are going to assume that the length of each pixel is 1 by 1. So it will be easy to write it here. So G1 will be 1, 1, 1, 1, and then 0 everywhere. The second line will be, the G2 will be 0, 0, 0, and then 1, 1, 1, and 0, and so on. You can complete this matrix in this way. And it will be interesting also to divide this first projection to this second projection. This is first projection, projection 1 at angle 0, and projection 2 at angle pi over 2. So if you divide this, you also divide this matrix. So I can call this G1 and this one G2. 1 means at angle 0, 2 means at angle 2. So we have G1 is equal to H1 F. This is the matrix H1. And this is the matrix H2. And we have G2 equal to H2F. And we can also combine G1 and G2 in G, like here. G1 and G2. And we can combine also H to H1 and H2. And have G equal to HF. Through this exercise or through this example, what I wanted to show you is that I told you about adjoint operator of the Radon transform, and I told you that the adjoint operator in the finite dimension becomes the operator of transpose of the matrix. The operation of back projection that we noted before. If I define B, which is back projection, equal to H transpose G, in this particular case, you will see that this can be written as H1 transpose G plus H2 transpose G. And if you look at what is